Hello everyone, I'm honored to have this opportunity to introduce our research to you here. I'm Chen Wei from Huazhong University of Science and Technology. The title of this presentation is A New Insight into Chemical Reactions Between Biomass and Alkaline Additives During Pyrolysis Process. It's divided into 4 parts here. The first is a simple background introduction. Biomass is the only carbon-containing renewable resource in nature that can be directly converted into green liquid fuel and valuable chemicals, and plays an important role in the future energy structure and carbon emission reduction. Pyrolysis can realize the utilization of the whole components of biomass, which is one of the most promising and efficient conversion pathways. Alkaline and alkaline metals such as potassium, sodium, calcium, and magnesium existing in biomass significantly influence the pyrolysis process. Understanding the effect mechanism of alkaline and alkaline metals is critical for better utilization of biomass. Many researchers have investigated the effect of alkaline additives on biomass catalytic pyrolysis. DeBlasey found that potassium hydroxide lowered the decomposition temperature of wood by 45 to 70 K. Now Kowalski reported that potassium acetate promoted the generation of phenol and cyclopentin derivatives. Fu pointed out that potassium hydroxide, potassium carbonate, and potassium bicarbonate increased furanic compounds, while decreased the level glucosamine during cellulose pyrolysis. However, due to the lower ending amounts of additive, the chemical reaction between biomass and alkaline additives are usually ignored. Zhou added 20 weight percent potassium hydroxide to biomass and found that hydrogen yield increased greatly. Wang reported that acids and aldehydes disappeared with the addition of 22 weight percent calcium hydroxide. However, no detailed analysis was made about the biochar properties. It led to the lack of the chemical reaction information about biomass and alkaline additive. A number of researchers have pointed out that these additives had activation effect on carbon materials, but the activation temperature was over 700 degrees Celsius, and they mainly focused on the effect of additive on carbon element. However, biomass pyrolysis usually at 500 to 600 degrees Celsius, and biomass contained over 40 weight percent oxygen. The influence of additives on oxygen-containing species in biomass is unknown. It's still not clear that the chemical reaction pathway between biomass and alkaline additives. Thus, in this study, we focused on chemical reaction between biomass and alkaline additives during pyrolysis process. Then, it's the pyrolysis. Bamboo waste was chosen as feedstock. 7 alkaline additives was chosen here. They are potassium hydroxide, potassium carbonate, potassium bicarbonate, potassium acetate, sodium hydroxide, calcium hydroxide, and magnesium hydroxide. Pyrolysis experiment was carried out in fixed bed system. The system consisted of a feeding unit, a fixed bed reactor, a condensing unit, and a gas cleaning and drain unit, with temperature and gas flow controllers. Liquid nitrogen condensing system was used to collect bioil, to precisely quantify bioil, Well, as water mix condensing system was used to analyze gas. Pyrolysis temperature is 600 degrees Celsius. Reaction time is 30 minutes. Mass ratio of alkaline additive and bamboo is 1:2. The third part is the results and discussion. It could be found that the mass balance was good. It should be pointed out that here, the alkaline additives was presumed to not react with biomass. However, to remove the effect of additives' direct decomposition, the blank experiments of additives pyrolysis alone were performed at the same conditions. Potassium hydroxide, potassium carbonate, and sodium hydroxide show high thermostability. Potassium bicarbonate, potassium acetate, calcium hydroxide, and magnesium hydroxide occurred some decomposition. To better understand the product's distribution, biochar was treated by acid washing to remove the inorganic compositions left, and the effect of additives pyrolysis has been removed. Biochar and gas yield increased, while bio-oil yield decreased largely. For potassium hydroxide and sodium hydroxide, the total yield is less than 100%, indicating that organic compounds converted to inorganic compounds. For potassium carbonate, potassium acetate, calcium hydroxide, and magnesium hydroxide, the total yield is over 100%, indicating that additives decomposed into pyrolytic products. For gas-releasing properties, alkaline additives show different properties. Potassium hydroxide and sodium hydroxide addition, hydrogen yield increased over 9 times. For potassium carbonate, carbon dioxide yield increased nearly 4 times. For potassium acetate, methane yield increased nearly 2 times. For calcium hydroxide, carbon monoxide increased over 2 times. For bio-oil compositions, with the introduction of alkaline additives, phenols and hydrocarbons increased significantly. Oxygen-containing species and acetic acid decreased largely. The selectivity of non-methoxyphenols increased greatly, even could reach 100%. Physical-chemical properties of biochar after washing were also explored in detail. Alkaline additives decreased carbon and hydrogen carbon of biochar, while increased the oxygen content. It indicated that alkaline additives could react with biomass and added more oxygen in biochar. Specific surface area increased greatly, reaching over 700 square meters per gram. In order to understand the oxygen-containing group evolution, the biochar was analyzed by XPS. From the full spectrum of biochar, it could be found that the inorganic compositions in biochar had been removed completely after washing. After the introduction of additives, hydroxyl and S groups replaced carbonyl groups to become the major oxygen-containing species, while the relative content of carbonyl groups reduced significantly. Other biochar also showed the similar distribution. However, the absolute content of oxygen-containing species in biochar showed some different change tendency. With the introduction of potassium hydroxide, potassium carbonate, potassium bicarbonate, potassium acetate, and sodium hydroxide, the yield of all oxygen-containing groups in biochar increased significantly. especially hydroxyl and ester groups, and ether bond. For calcium hydroxide and magnesium hydroxide, the yield of ester, hydroxyl, and carboxyl groups increased significantly, but the carbonyl group's yield decreased largely. In order to comprehensively explore the evolution properties of alkaline additives during biomass pyrolysis process, XRD patterns of biochar before and after washing were performed. Potassium hydroxide, potassium bicarbonate, and potassium acetate were consumed completely and formed the new compound potassium carbonate. Sodium hydroxide was also completely converted into sodium carbonate. Most calcium hydroxide was transformed into calcium oxide, and magnesium hydroxide was also completely converted into magnesium oxide. Moreover, the two peaks of biochar after washing were broad, indicating the mean carbon structure was amorphous carbon. Based on above discussion, the possible chemical reaction pathway between biomass and alkaline additives during pyrolysis process was proposed. During biomass pyrolysis, additives could react with the higher active oxygen-containing species in biomass. It removed oxygen-containing groups, accompanying the release of small molecule free radicals, and generated large amounts of vacancies. Additives can also etch the carbon fragments to form vacancies, accompanying the generation of hydrogen protons. Then some anions of alkaline additive quickly occupied these vacancies to form new oxygen-containing groups in biochar, mainly including hydroxyl, ester, and carboxyl groups. Meanwhile, alkaline additive converted to more stable structure. These processes fixed much oxygen in biochar, consequently increased biochar yield. At the same time, promoted biochar to form more developed porous structure. Furthermore, the free radicals could react with pyrolytic intermediates. Large amounts of non-methoxy phenols and aromatics were generated. It accompanied the release of carbon dioxide, carbon monoxide, hydrogen, and methane, leading to the increase of gas yield and decrease of bio yield. At last, in conclusion, during biomass pyrolysis process, alkaline additives not only show catalytic role, but also presented strong chemical reactions with biomass. The possible chemical reaction pathway between biomass and alkaline additives was proposed. Alkaline additives could react with high active oxygen-containing species and carbon fragments to form new oxygen-containing groups in biochar, and increase oxygen and surface area of biochar. Large amounts of free radicals generated could react with pyrolytic intermediates to generate high content of phenols and aromatics. Thanks for the support of National Nature Science Foundation of China, China Postdoctoral Science Foundation. Thanks for the Combustion Institute and our group. Thanks for your attention.